Okay, this is the second topic for this week's module. The title is SNR Dependence on Imaging Parameters and Image Contrast. So for this topic, I'll talk about very briefly the imaging field of view. The field of view also is covered in Hashemi in chapter 15. I sent out an announcement recently to ask you to read that. It's only 3 pages long, so it should be pretty quick reading. But the main focus of the topic will be the dependence of SNR per voxel on the imaging parameters, where these parameters are the number of averages, readout bandwidth, voxel dimensions, and so on. So the field of view, what is a field of view? It's really just the spatial dimensions over which to acquire the image. So here I'm just showing an image of a axial slice through a kiwi fruit, and field of view y in this direction. Take this as the y direction, take this as the x direction. And an important relationship is how the field of view is related to the bandwidth. So bandwidth is just really a range of frequencies. Because if you look at the image, remember we made this image using gradients, so we need some gradient to spatially encode the signal. And how is that? What's the gradient strength needed to make an image that such as a actual slice through a kiwi fruit, which is very small? Well, here I'm showing that the frequency, this relation field of view in the x direction is related to or equals the bandwidth divided by the gyromagnetic ratio times the gradient in the x direction. So F max here at this point is equal to gamma gx times field of view over 2. And in this region you'd have minus F max. So along this green line is the gradient, and along this green line are different frequencies because you have the gradient. So the bandwidth is the difference in the difference between F max and negative F max, or 2 F max. Okay, so again, talking about the field of view, it's important because you can't just keep, if you want to image, keep imaging things that are very small. As you keep getting smaller and smaller, let's go back to this real quick. If you keep imaging things that are smaller and smaller, your bandwidth has to increase. In order for your bandwidth to increase, your gradient has to be stronger. So there comes a certain limit, right, where your gradients just can't physically provide enough magnetic field gradient, because the amplifiers which drive the electrical current into the gradient coil can't put out enough power, and the actual wires that make up the gradient coil can't handle enough current, so they would just burn out. So you're imaging small things like, let me show this again, like this kiwi fruit. You really need high performance gradients, and this image was acquired in a 7 Tesla research magnet, and most of these research machines have very strong gradients. So you might be able to get something like this on a clinical machine, but it may not look as nice. The spatial resolution will be probably less, and we'll talk about spatial resolution soon. Okay, so now into the SNR dependence on the read direction parameters. So let's go back and just take a brief look again at some part of a gradient echo sequence, because I want to define for you here this delta t. Okay, so the delta t here are the samples, of the space between the samples during the analog to digital converter time that it's on. So how fast are we sampling? So that's delta t. T sub s is a total time that we are sampling. Okay, so these two symbols I'll be using throughout in different slides. So I'm just highlighting that here. And so what are some important read direction relationships? Well, the sample time, total sample time, is equal to the total number of samples in k-space times the width, or how fast you're sampling. The field of view in the x direction is equal to the number of samples in the k-space divided by, or I'm sorry, multiplied by the pixel, or the voxel width in the x direction. Similarly with field of view y and field of view z, the bandwidth in the read direction is just 1 over delta t, because bandwidth is in hertz and t is in seconds, which equals gamma bar gx lx. Okay, well, lx is actually field of view x, so those are the same. Bandwidth per voxel is bandwidth read over nx. So a few different cases here to show how the SNR is changing, or how you can change the SNR by changing certain read direction parameters. So the first case here is just a reference case where you have a certain pixel width in x, or voxel width in x, a certain number of samples in x, a certain field of view, a certain gradient strength, a certain sample time width, and a certain length, or total time that you're sampling. So this first case is bold text because it's my reference case where your SNR is 1. So now as we progress to different situations where, for example, here we've reduced the number of samples, but we've also reduced the field of view in the x direction, we have the same SNR. Case 3, we've doubled the number of samples, but we've also doubled the field of view, and we reduced the sample time, or the sample width, which keeps our SNR the same. Now let me click through here. Reference. So 2 and 3 are called data reduction and oversampling, and the reason you do data reduction and oversampling is to avoid what's called a phase wrap, or an aliasing artifact, and we'll talk more about that kind of artifact when we just on the module that we're going to have an entire module on artifacts. Okay, so now what happens when we degrade the spatial resolution? Well, so cases 4 and 5, we're degrading the spatial resolution by doubling the size of the voxel in the x direction. What else do we do? Well, for this case 4, we reduce the number of samples in k-space. We also reduce the amount of time we're sampling, which increases the SNR a little bit by root 2, or that's about 41%. But we can also do something else. We can reduce the resolution, by reducing the number of samples, and reducing the strength of the read gradient, and by doubling the time, the spacing between samples, while keeping the total time fixed, which increases the SNR by 2. So 6, 7, 8, 9, I won't go through in detail, but to show just in general that case 6, 7, 8, 9 are related to improving spatial resolution. And so when you improve spatial resolution, you always end up reducing your SNR. Okay. With these other, and again, we're just talking in terms of the read direction parameters here. So that's not for every case. I mean, again, just with regard to read direction parameters, if you increase your spatial resolution, it's going to be a slight, either a slight degradation in SNR or a severe degradation in SNR. Okay, so just I want to talk about now briefly SNR and 2D imaging in general. And this equation is here just as a general proportionality of the SNR per voxel in a 2D image. So it's proportional to the voxel width in X, the voxel width in Y, and TH, which is the slice thickness. So that's really, you could think of that as the voxel width in Z, but in 2D imaging we don't specify explicitly a voxel width in Z. We just explicitly specify a slice thickness. And we're also multiplying by the square root of the number of k-space samples in the y direction times TS. And remember, T sub S is the number of samples in X in k-space times delta T. And dx is the field of view X over nx. So here another example. Well, this is the same image from before, but just wanted to show the field of view. So this is 5 centimeters by 5 centimeters, and the number of samples in X is equal to the number of samples in Y is equal to 256. So this is a common excuse me, nx and ny number. So whoops, you can I think we've talked about a little bit before why we would choose 256 or 128 or 64, because those are powers of 2 in the Fourier transform, or more specifically the fast Fourier transform likes powers of 2. So when the fast Fourier transform operates on data sets that are powers of 2, it's an efficient operation, makes the reconstruction process faster. So here are some examples, and specifically towards showing you how SNR improves as a square root of the number of acquisitions. So look at this. Look at these 3 images. These are the same slice through the same fruit. So these images are then registered. So what I'm showing also is, well, anyway, just for your information, these images are also at the same grayscale level. So maybe we can talk a little bit about that during the chat this week. What does grayscale mean? Because when you're comparing images, most MRI, or almost all MRI images, are black and white. If you're going to compare these images, you have to make sure that you're looking at them at with the same contrast settings, or what are called window or level settings. So by placing them into this type of so-called montage, the window and level settings are the same. So now I can compare them. So if you look at the image here with 2 averages, we can see just by eye that the noise floor is there, and we can see as we go to number of averages equal to 4, that goes down, the noise floor goes down, number of averages 8, noise floor goes down again. So we can see by eye an improvement. And the SNR calculated by these ROIs, where this ROI here is a noise, and then I drew an ROI to include most of the fruit. And I use the same ROIs for each one to calculate the SNR. So theoretically, we know that going from 2 to 4, we should see an increase in SNR of root 2. Yes, so we should see theoretically 10.7, and that's how it worked out, which is nice. Now, going from 2 to 8, we should see an increase of square root of 4, because we've gone from 2 averages to 8 averages, so we've increased our number of acquisitions by 4. So by taking the square root of 4, we get 2, so our SNR should have doubled. So our theoretical SNR was 15.2. We almost achieved that. So you're not always going to get the theoretical maximum SNR improvement, but you should get very close to it. Now, what about as a function of slice thickness? Let me go back here and make sure I didn't skip anything. Okay. As a function of slice thickness, so in this example, first let's look at the image. This image has a thickness of 2 millimeters, then I went from 3 and then to 4. So I want you on your own to look closely at these images and to see what's happening. Okay, there are some very subtle differences just in terms of what you can see in the image. But in terms of the SNR, we see that for the what we should expect, the image with the lowest or the thinnest slice has the lowest SNR. So, and again, I use the same ROIs to measure the SNR, where, as we talked about before in the previous topic, the SNR is calculated as the mean of the signal, which is from this ROI, the mean being the mean value of all these pixel intensities divided by the standard deviation of all the intensities in the noise ROI. Again, it's a standard deviation that's important. So theoretically, we should be, for a thickness of 3 millimeters, we should be at 43.4. Okay, we've gone up by 1/3. Here, remember, the equation that I showed you before, the SNR in 2D imaging is directly proportional to the slice thickness. So if I double my slice thickness, I go from 2 to 4, I should double the SNR. So theoretically, I should be, in this image, my SNR should be twice what it is at the 2 millimeter image, or 57.8. See, we almost make it. So that's just a quick check. So, you know, for example, if this number was, say, 42, then we know either we didn't, the scan, when the scan occurred, the thickness wasn't actually 4 millimeters, or maybe there's some other imaging parameter in there that was not held constant between the 2 millimeter scan and the 4 millimeter scan. But it appears that worked correctly in this case. So one quick slide about spatial resolution. The two images here are from different scans, so you really don't want to compare the contrast directly. On the left is actually from a gradient echo sequence. On the right is from a fast spin echo sequence. And the reason I use these sequences was to calculate the actual T1 and T2 star times of the fruit. But what it's important for now is to notice when you look at an image with 256, for example, 256 by 256 matrix, compare that to an image of the same object with the same field of view but a reduced matrix size. Just by eye, clearly you see difference in what objects you can see and what you cannot see. And a common way to kind of quantify that that quality of spatial resolution is to take a profile or draw a line through an image and look at the profile. So what I've done is I've drawn a line, this white line. It's may be hard for you to see. I've drawn a white line around here, and I'm showing on the line this curve down here, this plot is just the pixel values going from this point around this line and back to this point here. So you can see these peaks and troughs are from this little space here between, well, I don't know what these things are inside the fruit, but you know, you're going from high pixels here to low, high to low, high to low. Now I have the same, this is an approximately the same ROI. I wasn't able to physically draw the same one, but if you look at the same region in the lower spatial resolution image, you can see that the profile is much choppier, so indicating that we can't really resolve those little tiny spaces between these pieces of fruit structure. Okay, so another important thing I want to get through, and I'll try to make this pretty quick, but not too quick, as it's very important, is image contrast and contrast to noise. Contrast to noise is really the true measure of how good, how qualitatively good your image is, because you can have fantastic signal to noise, but if you don't have contrast between two tissues, then really your image is not very helpful, right? So just a really basic definition of contrast and contrast and noise. Contrast is really just the difference between the signals in one tissue, say tissue A, and the signal in tissue B. Contrast and noise is the contrast between A and B divided by the standard deviation of the noise, or sigma 0 here, which just ends up being the SNR of tissue A minus the SNR of tissue B. So you may wonder then, well, how much contrast is enough? How much contrast do we need between two tissues in order for the human eye to be able to tell, one tissue from the next? And it turns out back, I believe it was in 1948, person, I don't remember his first name, but his last name was Rose, came up with, of course, the Rose criterion, which says that a detection SNR threshold of about 3 to 5 was found to be required for object recognition. So he did this by having people look at small objects on a television screen, and just kept degrading the SNR until people were no longer able to discern between the objects. And that's a rough, very rough description of what he did. So for people who may know about that experiment, I'm sorry if I didn't get that exactly right, but that's just my from memory. Okay, so really the most basic contrast mechanisms are based on the difference in spin density, rho naught, and T1 and T2 times. And in particular, for a gradient echo pulse sequence like we've been talking about with a 90-degree flip angle, the contrast between two tissues is given by this equation. So for spin density weighting, what we would need to do, so if we just want our image contrast to be based on the spin density between two tissues, we would need to make sure that TE is much less than the TE time in the pulse sequence is much less than T2 star of tissue A and B, and the TR is much greater than the T1 of tissues A and B, so that these conditions are satisfied. Now if we want to do T1 weighting, we really need just to make sure that TE is much less than T2 star of A and B. And then for TR, we can really optimize the TR, because we can then, using this condition, we can come up with an expression for the contrast. And then I note here, to maximize the T1 contrast, we can maximize this equation for contrast with respect to TR. And then from calculus, you just differentiate this equation with respect to TR and set it equal to 0, which would give you this equation. From this, you can just solve for TR, and you end up with this equation. So that's, now, of course, you'd have to go through certain steps experimentally to determine what rho naught is, to determine what T1 is. And sometimes that's, you don't have time to do that in the clinic. Sometimes you can take a guess. From experience, you would know. So, and I'll show you some examples later on. But that's just a basic procedure to get an optimal TR. Now what about T2 star? Well, you go through a similar steps. So for a T2 star weighted image, conditions on conditions on TR is that TR must be much greater than T1 AB, and then your contrast then becomes a function of TE. So now we can do the same thing as we did with T1. We just differentiate similar thing, differentiate the contrast with respect to TE, set it equal to 0, and then we solve for TE. We come up with this equation. Okay, so let's look at an example here. So what I did was I took, in the beginning, before I took these images, I did a scan to determine the T1 of the fruit, where the T1 was, I determined the T1 of some pixels in this bright region here. And that ended up being about 1,700 milliseconds. I took a separate scan, which was designed to calculate the T2 star, and that number ended up being 22 milliseconds. So based on those numbers, I could then set my TR and TE to be approximately equal, or I'm sorry, my TR in this case and my TE to give about only proton density weighting. Really, so for TR, you want to be about 5 times T1, and I'm almost there. And remember, so the longer the TR, the longer the scan, so I wanted to keep the scan a little bit shorter. Now for T1 weighting, I wanted my TE to be much less than T2 star, but TR just has to be moderately, quote unquote, moderately short. So that's why I selected 500. Again, that was just a guess, really. This is not the optimal TR. I did not, unfortunately, have the time to optimize that. And for the T2 image, you want to keep TR long, which it is here. But notice a change in TE. Now the TE is much longer than for these two cases here, and it's longer than the T2 star. Again, this is not the optimal TE. I picked it kind of based on experience. So so if you look closely at these images, the proton density weighted image doesn't look that much different from the T1, but there are some differences. So go through carefully. For example, look at these parts of the seeds. They're brighter here, and out here you see these dots here are brighter, and clearly the contrast between these two and the T2 is much different. Okay, so that's going to be it for this topic. I'll put the PowerPoint slides on Blackboard as well for you to review at your convenience. And if you have any questions about the video, please send me an email. Thank you.